He was born in a time when science was still a mystery. He wrote formulas that explained the movement of the stars, the curve of rivers, and the sound of the wind. Even blind, he continued to see the infinite. This is the story of Leonhard Euler, the man who deciphered the language of God.
The Greatest Mathematicians of All Time, Episode 18, Leonhard Euler. Euler was born on April 15, 1707 in Basel, Switzerland, and died on September 18, 1783 in St. Petersburg. Leonhard Euler's father was Paul Euler. Paul Euler studied theology at the University of Basel and attended the lectures of Jacob Bernoulli. In fact, Paul Euler and Johann Bernoulli lived in Jacob Bernoulli's house while they were undergraduates in Basel. Paul Euler had become a Protestant pastor and married Margaret Brucker, the daughter of another Protestant pastor. His son Leonhard Euler was born in Basel, but the family moved to Rheims when he was 1 year old, and it was in Rheims, not far from Basel, that Leonhard was raised. Paul Euler had, as we mentioned, some mathematical training, and was able to teach his son elementary mathematics, in addition to other subjects. Euler was sent to school in Basel, and during that time lived with his maternal grandmother.
This school was quite poor, according to all accounts, and Euler learned no mathematics there. However, his interest in mathematics was certainly awakened by his father's teachings, and he read mathematical texts on his own and had some private lessons. Euler's father wanted his son to follow him into the church and sent him to the University of Basel to prepare for the ministry. He entered the university in 1720 at the age of 14, first to obtain a general education before proceeding to more advanced studies. Johann Bernoulli soon discovered Euler's great potential for mathematics in private lessons that Euler himself arranged. In one of his unpublished autobiographical writings, Euler himself recounts, "I soon found an opportunity to be introduced to a famous professor, Johann Bernoulli. It is true that he was very busy and therefore flatly refused to give me private lessons, but he gave me much more valuable advice to begin reading more difficult mathematics books on my own and studying them as diligently as possible. If I encountered any obstacle or difficulty, I was allowed to visit him freely every Sunday afternoon, and he kindly explained everything I could not understand."
In 1723, Euler completed his master's degree in philosophy, having compared and contrasted the philosophical ideas of Descartes and Newton. He began his studies in theology in the autumn of 1723, following his father's wishes. But although he was a devout Christian throughout his life, he could not find the enthusiasm for the study of theology, Greek, and Hebrew that he found in mathematics. Euler obtained his father's consent to switch to mathematics after Johann Bernoulli used his persuasion. The fact that Euler's father had been friends with Johann Bernoulli during their undergraduate days undoubtedly made the task of persuasion much easier. Euler completed his studies at the University of Basel in 1726. He studied many mathematical works during his time in Basel, and Collinger has reconstructed many of the works that Euler read on the advice of Johann Bernoulli. They include works of Varignon, Descartes, Newton, Galileo, Van Schoten, Jacob Bernoulli, Hermann, Taylor, and Wallace. By 1726, Euler already had one paper in print, a short article on isochronous curves in a resisting medium.
In 1727, he published another paper on reciprocal trajectories and submitted an entry for the 1727 Grand Prize of the Paris Academy on the best arrangement of masts on a ship. The 1727 prize went to Bouguer, a specialist in mathematics related to ships, but Euler's essay earned him second place, which was a fine achievement for the young graduate. However, Euler now had to find an academic appointment, and when Nicolaus II Bernoulli died in St. Petersburg in July 1726, creating a vacancy there, Euler was offered the position which would involve him teaching applications of mathematics and mechanics to physiology. He accepted the position in November 1726, but stated that he did not want to travel to Russia until the following spring. He had two reasons for delaying. He wanted time to study the topics related to his new position, but he also had a chance of a position at the University of Basel, since the professor of physics there had died. Euler wrote a paper on acoustics, which became a classic, in his attempt to be selected for the position, but he was not chosen to proceed to the stage where lots were drawn to make the final decision on who would occupy the chair. Almost certainly his youth, he was 19 years old at the time, was against him.
This decision ultimately benefited Euler because it forced him to move from a small republic to an environment more suitable for his brilliant research and technological work. As soon as he learned that he would not be appointed to the chair of physics, Euler left Basel on April 5, 1727. He traveled down the Rhine by boat, crossed the German states by postal carriage, and then by boat from Lübeck, arriving in St. Petersburg on May 17, 1727. He joined the St. Petersburg Academy of Sciences 2 years after its founding by Catherine I, wife of Peter the Great. Through the requests of Daniel Bernoulli and Jacob Hermann, Euler was appointed to the Mathematics and Physics division of the Academy, instead of the physiology position he had originally been offered. In St. Petersburg, Euler had many colleagues who would provide him with an exceptional environment. Nowhere else could he have been surrounded by such a group of eminent scientists, including the analyst and geometer Jacob Hermann, a relative, Daniel Bernoulli, with whom Euler was connected not only by personal friendship, but also by common interests in the field of applied mathematics, the versatile scholar Christian Goldbach, with whom Euler discussed various problems of analysis and number theory, F. W. M. Meyer, working on trigonometry, and the astronomer and geographer J. N. Del Isle.
Euler served as a medical lieutenant in the Russian Navy from 1727 to 1730. In St. Petersburg, he lived with Daniel Bernoulli, who, already unhappy in Russia, had requested that Euler bring him tea, coffee, brandy, and other delicacies from Switzerland. Euler became a professor of physics at the Academy in 1730. And as this allowed him to become a full member of the Academy, he was able to resign his post in the Russian Navy. Daniel Bernoulli held the senior chair in mathematics at the Academy, but when he left St. Petersburg to return to Basel in 1733, it was Euler who was appointed to this senior chair of mathematics. The financial improvement that came from this appointment allowed Euler to marry, which he did on January 7, 1734, marrying Katharina Gsell, the daughter of a painter at the St. Petersburg Gymnasium. Katharina, like Euler, was from a Swiss family. They had 13 children in total, although only 5 survived infancy.
Euler claimed to have made some of his greatest mathematical discoveries while holding a baby in his arms, with other children playing around his feet. We will examine Euler's mathematical achievements later, but at this point it is worth summarizing Euler's work during this period of his career. After 1730, he undertook state projects related to cartography, scientific education, magnetism, fire engines, machinery, and shipbuilding. The core of his research program was now established: number theory, infinitesimal analysis, including its emerging branches, differential equations, and calculus of variations, and rational mechanics. He saw these three fields as intimately interconnected. Studies of number theory were vital to the foundations of calculus, and special functions and differential equations were essential to rational mechanics, which provided concrete problems. The publication of many papers and his book Mechanica, 1736-37, which extensively presented Newtonian dynamics in the form of mathematical analysis for the first time, put Euler on the path to great mathematical work. Euler's health problems began in 1735, when he had a severe fever and almost lost his life. However, he concealed this news from his parents and members of the Bernoulli family in Basel until he recovered.
In his autobiographical writings, Euler states that his vision problems began in 1738 with excessive strain due to his cartographic work, and that by 1740 he had lost one eye and the other was in danger of the same fate. However, Challenger argues that Euler's vision problems almost certainly began earlier and that the severe fever of 1735 was a symptom of eye strain. He also argues that a 1753 portrait of Euler suggests that at that stage the vision in his left eye was still good, while that in his right eye was poor but not completely blind. Challenger suggests that Euler's left eye became blind from a later cataract rather than eye strain. By 1740, Euler had a very high reputation, having won the grand prize of the Paris Academy in 1738 and 1740. On both occasions, he shared the first prize with others. Euler's reputation led to an offer to go to Berlin, but at first he preferred to remain in St. Petersburg. However, political turmoil in Russia made the position of foreigners particularly difficult and contributed to Euler changing his mind. Accepting an improved offer, Euler, at the invitation of Frederick the Great, went to Berlin, where an Academy of Sciences was planned to replace the Society of Sciences. He left St. Petersburg on June 19, 1741, arriving in Berlin on July 25. In a letter to a friend, Euler wrote, "I can do exactly what I want in my research. The king calls me his professor, and I think I am the happiest man in the world." Even in Berlin, Euler continued to receive part of his salary from Russia. With this remuneration, he bought books and instruments for the St. Petersburg Academy, continued to write scientific reports for them, and educated young Russians.
Maupertuis was the president of the Berlin Academy when it was founded in 1744, with Euler as director of mathematics. He substituted for Maupertuis in his absence, and the two became great friends. Euler performed an unbelievable amount of work for the Academy. He supervised the observatory and botanical gardens, selected personnel, oversaw various financial matters, and in particular managed the publication of several calendars and geographical maps, the sale of which was a source of income for the Academy. The king also tasked Euler with solving practical problems, such as the 1749 project to correct the level of the Fenal Canal. At that time, he also supervised the work on the pumps and pipes of the hydraulic system at Sanssouci, the royal summer residence. This was by no means the limit of his duties. He served on the Academy Committee that dealt with the library and scientific publications. He served as an advisor to the government on state lotteries, insurance, annuities and pensions, and artillery. Furthermore, his scientific output during this period was phenomenal. During the 25 years spent in Berlin, Euler wrote approximately 380 articles. He wrote books on the calculus of variations, on the calculation of planetary orbits, on artillery and ballistics, extending Robin's book, on analysis, on shipbuilding and navigation, on the motion of the moon, lectures on differential calculus, and a popular science publication, Letters to a German Princess, 1768 to 1772.
In 1759, Maupertuis died, and Euler assumed the leadership of the Berlin Academy, although not the title of president. The king was in overall command, and Euler was now not on good terms with Frederick, despite initial favor. Euler, who had argued with D'Alembert on scientific matters, was disturbed when Frederick offered D'Alembert the presidency of the Academy in 1763. However, D'Alembert refused to move to Berlin, but Frederick's continued interference in the administration of the Academy led Euler to decide that the time had come to leave. In 1766, Euler returned to St. Petersburg, and Frederick was very annoyed by his departure. Shortly after his return to Russia, Euler became almost completely blind after an illness. In 1771, his house was destroyed by fire, and he managed to save only himself and his mathematical manuscripts.
A cataract operation shortly after the fire, still in 1771, restored his sight for a few days, but Euler seems to have failed to take the necessary precautions and became completely blind. Because of his remarkable memory, he was able to continue with his work in optics, algebra, and lunar motion. Surprisingly, after his return to St. Petersburg, when Euler was 59 years old, he produced almost half of his works despite complete blindness. Euler, of course, did not achieve this remarkable level of production without help. He was assisted by his sons, Johann Albert Euler, who was appointed to the chair of physics at the St. Petersburg Academy in 1766, becoming its secretary in 1769, and Christoph Euler, who had a military career. Euler was also assisted by two other members of the Academy, W. L. Kraft and A. J. Lexell, and by the young mathematician N. Fuss, who was invited to the Academy from Switzerland in 1772. Fuss, who was Euler's grandson, became his assistant in 1776.
Yushkevich writes, "The scientists who assisted Euler were not mere secretaries. He discussed the general scheme of the works with them, and they developed his ideas, calculating tables, and sometimes compiling examples." For example, Euler credits Albrecht, Kraft, and Lexell for their help with his 775-page work on the motion of the moon, published in 1772. Fuss helped Euler prepare more than 250 articles for publication during a period of about 7 years in which he served as Euler's assistant, including an important work on insurance that was published in 1776. He also wrote a eulogy for Euler. Yushkevich describes the day of Euler's death. On September 18, 1783, Euler spent the first half of the day as usual. He gave a mathematics lesson to one of his grandsons, did some calculations with chalk on 2 blackboards about the movement of balloons. Then he discussed the newly discovered planet Uranus with Lexell and Fuss. Around 5 o'clock in the afternoon, he suffered a cerebral hemorrhage and only said, "I am dying," before losing consciousness. He died around 11 o'clock at night. After his death in 1783, the St. Petersburg Academy continued to publish Euler's unpublished work for almost 50 years.
Euler's work in mathematics is so vast that a video of this nature can only give a very superficial account of it. He was the most prolific writer of mathematics of all time. He made great advances in the study of modern analytical geometry and trigonometry, where he was the first to consider sine, cosine, etc. as functions instead of chords as Ptolemy had done. He made decisive and formative contributions to geometry, calculus, and number theory. He integrated Leibniz's differential calculus and Newton's method of fluxions into mathematical analysis. He introduced beta and gamma functions and integrating factors for differential equations. He studied continuum mechanics, lunar theory with Clairaut, the three-body problem, elasticity, acoustics, the wave theory of light, hydraulics, and music. He laid the foundations of analytical mechanics, especially in his Theory of the Motions of Rigid Bodies, 1765. We owe to Euler the notation f of x for the function, 1734, e for the base of natural logarithms, 1727, I for the square root of -1, 1777, pi for the mathematical constant representing the ratio of a circle's circumference to its diameter, sigma for summation, 1755, the notation for finite differences, delta epsilon, and many others. Let's examine some of Euler's work in more detail. Firstly, his work in number theory seems to have been stimulated by Goldbach, but probably originated from the Bernoulli family's interest in the topic.
Goldbach asked Euler in 1729 if he was familiar with Fermat's conjecture that the numbers 2 to the power of n plus 1 were always prime if n was a power of 2. Euler verified this for n equals 1, 2, 4, 8, and 16, and later in 1732 showed that the next case, 2 to the power of 32 plus 1 equals 4,294,967,297, is divisible by 641 and therefore not prime. Euler also studied other unproven results of Fermat and, in doing so, introduced Euler's totient function, phi function. Later, in 1749, he proved another of Fermat's claims, namely that if A and B are co-prime, A squared plus B squared has no divisor of the form 4n minus 1. Perhaps the result that brought Euler the most fame in his youth was the solution to what became known as the Basel problem. This involved finding a closed form for the sum of the infinite series zeta of 2 equals the sum of 1 over n squared, a problem that had defeated many leading mathematicians, including Jacob Bernoulli, Johann Bernoulli, and Daniel Bernoulli. The problem was also studied unsuccessfully by Leibniz, Stirling, de Moivre, and others. Euler demonstrated in 1735 that zeta of 2 equals 1/6 pi squared.
In 1737, he proved the connection of the zeta function with the series of prime numbers, giving the famous relation that the zeta of S is equal to the sum from n equal to 1 to infinity of 1 divided by n raised to the power of S, and this is equal to the product taken over all prime numbers p of 1 divided by 1 minus p raised to the power of minus s. In 1739, Euler found the rational coefficients c such that the zeta of 2n is equal to c times pi raised to the power of 2n in terms of Bernoulli numbers. Other works by Euler on infinite series included the introduction of his famous Euler constant gamma in 1735, which he showed to be the limit of the sum of the fractions from 1 to 1 over n minus the natural logarithm of n as n tends to infinity. He calculated the constant gamma to 16 decimal places. Euler also studied Fourier series and, in 1744, was the first to express an algebraic function by such a series, when he presented the result: half of pi minus half of x is equal to the sum of the sine of x plus half of the sine of 2x plus 1/3 of the sine of 3x, and so on.
Like most of Euler's work, there was a considerable delay before the results were published. This result was not published until 1755. Euler wrote to James Stirling on June 8, 1736, telling him about his results on the sum of reciprocals of powers, the harmonic series, and Euler's constant, and other results on series. In particular, he wrote, "Regarding the summation of very slowly converging series, last year I gave a lecture to our Academy on a special method by which I provided the sums of many series with sufficient accuracy and with very little effort." He then describes what is now called the Euler-Maclaurin summation formula. 2 years later, Stirling replied telling Euler that Maclaurin will publish a book on fluxions. He has 2 theorems for summing series by means of derivatives of the terms, one of which is the same result that you sent me. Euler replied, "I have very little desire that anything should detract from the fame of the celebrated Mr. Maclaurin, since he probably discovered this theorem for the summation of series before me, and consequently deserves to be named its first discoverer. For I discovered this theorem about 4 years ago, at which time I also described its proof and application in more detail to our Academy." Some of Euler's results in number theory were mentioned above. Other important results of Euler in number theory include his proof of Fermat's last theorem for the case of n equals 3. Perhaps more significant than the result itself was the fact that he introduced a proof involving numbers of the form a plus b times the square root of minus 3. For integers a and b. Although there were problems with his approach, this eventually led to Kummer's important work on Fermat's last theorem and the introduction of the concept of a ring.
It can be said that mathematical analysis began with Euler. In 1748, in Introductio in Analysisem Infinitorum, Euler made Johann Bernoulli's ideas more precise in the definition of a function and stated that mathematical analysis was the study of functions. This work bases calculus on the theory of elementary functions instead on geometric curves, as had been done previously. Also in this work, Euler presented the formula: the exponential of ix is equal to the cosine of x plus I times the sine of x. In Introductio in Analysisem Infinitorum, Euler dealt with logarithms of a variable that takes only positive values, although he had discovered the formula: the natural logarithm of -1 is equal to pi multiplied by I in 1727. He published his complete theory of logarithms of complex numbers in 1751. Analytic functions of a complex variable were investigated by Euler in several different contexts, including the study of orthogonal trajectories and cartography. He discovered the Cauchy-Riemann equations in 1777, although D'Alembert had discovered them in 1752 while investigating hydrodynamics. In 1755, Euler published Institutiones Calculi Differentialis, which begins with a study of the calculus of finite differences. The work provides a complete investigation of how differentiation behaves under substitutions. In Institutiones Calculi Integralis, 1768 to 1770, Euler made a complete investigation of integrals that can be expressed in terms of elementary functions. He also studied the beta and gamma functions, which he first introduced in 1729.
Legendre called them Eulerian integrals of the first and second kind, respectively, while Binet and Gauss called them the beta function and gamma function, respectively. In addition to investigating double integrals, Euler considered ordinary and partial differential equations in this work. The calculus of variations is another area in which Euler made fundamental discoveries. His work, Method for Finding Curved Lines, published in 1740, initiated the proper study of the calculus of variations. Carathéodoe considered this to be one of the most beautiful mathematical works ever written. Problems in mathematical physics led Euler to an extensive study of differential equations. He considered linear equations with constant coefficients, second-order differential equations with variable coefficients, power series solutions of differential equations, a method of variation of constants, integrating factors, a method of approximating solutions, and many others. When considering vibrating membranes, Euler was led to Bessel's equation, which he solved by introducing Bessel functions. Euler made substantial contributions to differential geometry, investigating the theory of surfaces and curvature of surfaces. Many of Euler's unpublished results in this area were rediscovered by Gauss. Other geometric investigations led him to fundamental ideas in topology, such as the Eulerian characteristic of a polyhedron. In 1736, Euler published Mechanica, which provided a major advance in mechanics.
As Yushkevich writes, the distinctive feature of Euler's investigations in mechanics, compared to those of his predecessors, is the systematic and successful application of analysis. Previously, the methods of mechanics were predominantly synthetic and geometric. They required a very individualized approach to distinct problems. Euler was the first to recognize the importance of introducing uniform analytical methods into mechanics, thus allowing its problems to be solved clearly and directly. In Mechanica, Euler considered the motion of a point mass both in a vacuum and in a resistive medium. He analyzed the motion of a point mass under a central force and also considered the motion of a point mass on a surface. In this latter topic, he had to solve several problems of differential and geodesic geometry. Mechanica was followed by another important work in rational mechanics, this time Euler's two-volume work on naval science. Distinguished in both theoretical and applied mechanics, it addresses Euler's intense preoccupation with the problem of ship propulsion. He applies variational principles to determine the ideal design of ships and establishes for the first time the principles of hydrostatics. Here, Euler also begins to develop the kinematics and dynamics of rigid bodies. introducing in part the differential equations for their motion. Of course, hydrostatics had already been studied since Archimedes, but Euler presented a definitive version. In 1765, Euler published another important work on mechanics, Theory of the Motion of Solid Bodies, in which he decomposed the motion of a solid into rectilinear and rotational motion. He considered Euler angles and studied rotational problems motivated by the problem of the precession of the equinoxes.
Euler's work on fluid mechanics is also noteworthy. He published a series of important works throughout the 1750s, establishing the main formulas for the topic: the continuity equation, Laplace's velocity-potential equation, and Euler's equations for the motion of an incompressible and inviscid fluid. In 1752, he wrote, "However sublime the researches on fluids that we owe to Messrs. Bernoulli, Clairaut, and d'Alembert may be, they flow so naturally from my two general formulae that one cannot sufficiently admire this agreement of their profound meditations with the simplicity of the principles from which I extracted my two equations." Euler contributed to knowledge in many other areas, and in all of them he employed his mathematical knowledge and skill. He carried out important work in astronomy, including the determination of the orbits of comets and planets from a few observations, methods for calculating the parallax of the Sun, the theory of refraction, and consideration of the physical nature of comets. His most outstanding works, for which he won many prizes from the Académie des Sciences in Paris, deal with celestial mechanics, which especially attracted the scientists of the time. In fact, Euler's lunar theory was used by Tobias Mayer in the construction of his lunar tables. In 1765, Mayer's widow received £3,000 from Great Britain for the contribution of the tables to the problem of determining longitude, while Euler received £300 from the British government for his theoretical contribution to the work. Euler also published on the theory of music, in particular Tentamen Novae Theoriae Musicae in 1739, in which he attempted to make music start from mathematics and deduce in an orderly manner from correct principles everything that can make the combination and blending of tones pleasing.
However, the work was, for musicians, very advanced in mathematics, and for mathematicians, very musical. Cartography was another area in which Euler became involved when he was appointed director of the geography section of the St. Petersburg Academy in 1735. His specific task was to help Delisle prepare a map of the entire Russian Empire. The Russian Atlas was the result of this collaboration and was published in 1745, consisting of 20 maps. Euler, in Berlin at the time of its publication, proudly noted that this work placed the Russians well ahead of the Germans in the art of cartography. When Euler's sight failed, the world lost a pair of eyes, but gained a new way of seeing the universe. Because some men do not see with their eyes, they see with their soul. Leonhard Euler, the man who saw the infinite. If this story inspired you, leave a comment with the name of the next genius you want to learn about.